Big hint on a cubic equation here. There's a single natural number solution. Now by natural number solutions, I do mean x equals 2. 1, 2, 3, and so on. Just the positive integers. Now, it turns out there's around 36, there's exactly 36 divisors right here. $36 divisors of this constant term of 41,650. $36 divisors. Now that's a lot of numbers to check. There's something called the rational number theorem. There's something called the rational number theorem where we could check all 36 of those divisors, but that would be computationally onerous. Now you're better off here actually just doing this. Now this is also computationally burdensome, but it's not quite as bad. You just divide by 2. Notice you have a 5 and divide by 5 and so on. So this is something that's not hard, but rather tedious. Now notice I rewrote the expression. This statement up here is absolutely equivalent to this statement, and then you can factor the left-hand side, and so we're already looking pretty good here if we can get the squared factors of 41,650, right? Well, notice right here, from this process right here, we have 2 as a prime factor. This is called a prime tree, by the way. 5, 7, 5, twice. Let's see here. We have 7, 17 going on here. Okay. Now, why is that helpful? Because you can see we have 5 squared right here. This amounts to 5 squared right here. And this is these two terms, these two guys right here in the tree are actually leaves in the tree, I guess. 7 squared. Then we have 2 and 17 is single primes. And so that means we can rewrite this in a very cool way here. You can write this as 5 times 7 quantity squared. And then, of course, we have the 2 and the 17 left. And I'm leaving it that way. Just there's a uniqueness to it, and the computations are real easy when you get the numbers in the single digits like this. 2 times 17. So there we go. Now notice here, though, that leads this prime factorization is unique, notwithstanding the order, but that's okay because we have a squared factored expression right here, and so you literally can equate this. In other words, you can say that x, this is your x, right? So x would equal to 5 times 7. So x, just by comparison, is 35. Now notice right here you get the same thing. If you set x minus 1, now not that you need to do this, you already know the answer because of the uniqueness, but x minus 1 has to equal to 2 times 17. So in other words, we also get x minus 1 is equal to 2 times 17, which is equal to 34. Okay, and of course, that certainly implies that x is equal to 35. So y'all, this is the answer. X equals 35 is the solution to the problem. And that ends this video.